All right. Hey, let me try another video solution. This one is out of chapter 22, number 15. Has to do with our heat engines here. And in this case, it's a turbine engine, so it's an expansion of gas. So what you do is you have gas compressed, and you actually then heat it or burn something, and get it really, really hot. Although in this case, it looks like it says argon, so we're not actually burning the argon, but somehow we get the argon compressed and really hot, and then we let it expand, pushing something, usually a turbine blade, but as it expands, it's doing work, and so that's how we build our heat engines. The expanding gases is doing the push. All right, so in 15, it says argon enters a turbine at a rate of 80 kilograms per minute. So there is the flow rate into our engine. Now that's also then telling us, really how many moles are there. So keep that in mind. They say the temperature is coming in at 800 degrees Celsius and at a huge pressure, 1.5 megapascals. Well, I guess I shouldn't say huge, but it's a big pressure for common things. It expands adiabatically. There's the key. We need to know how our gas is functioning. Is it expanding with constant temperature? No, apparently, because it says adiabatic. Is it expanding with constant pressure? Well, apparently no, because it just said it's adiabatic. So things that tend to expand really, really quickly, we kind of say they're adiabatic. They don't have time to transfer their heat. And that's not completely perfect. We do know when engine warms up, so obviously some heat must transfer, but for one particular gas, it's somewhat adiabatic. Okay. So as it pushes on the turbine blade and exits at a pressure of, so this would be what I might call the initial pressure as it comes out of the turbine engine. Now that it is expanded and done work, the pressure has dropped to 300 kilopascals. Okay, so there's our basic information for our engine. Okay, it says A, calculate the temperature at the exit. All right, well, the first thing going on in my mind is that since this is an adiabatic process, the initial pressure times the initial volume raised to a power of gamma equals some constant, and that same constant would be the final pressure times the final volume raised to that same power of gamma. Okay. Now, in this case, we know initial and final pressures. We even have temperature. So I'm kind of thinking the thing to do is to convert volume into temperature. And we could do that with the ideal gas law. So this would be nRT over P raised to a power of gamma. Now, of course, we're talking about initial, so I'll put initial temperature and I'll put initial pressure. I could do the same thing over here, final pressure. And then, again, final volume, let me convert that to final temperature. Let me come back to the question, because that's it, right? Calculate the temperature. Yeah, so we want to find that. Okay, now we can simplify this because this would be n to the gamma, but over here we would have n to the gamma, so that would cancel off. And this here would be r to the gamma, and this would be r to the gamma, so that would cancel off. Now, it looks like over here, we would still have initial temperature to a power of gamma, but down here we would have pressure to a power of gamma. Okay, and then if we worked in this one, and I'm not sure if it's better to move this one down or this one up. Maybe I'll move it down just because I know gamma is greater than 1. So I'm going to go initial pressure And gamma, when I move this down, it becomes -1, so this becomes gamma minus 1. Now this over here would be final temperature to a power of gamma over, and we can do the same thing, final pressure, and then again we would have gamma downstairs, and if we bring this pressure down, that's -1. Okay, so now we can actually put in our numbers and eventually solve here for final temperature. Now I like to do this in a couple of steps, but I'm going to put here that the initial temperature, now back here we said it was 800 Celsius. So we add 273 to it. Let's see, 200 makes 1,000, so that's going to be 1,073 raised to a power of gamma. Now maybe it's worth doodling over here on the top. Gamma is Cp over Cv. Now Cp, well, let me start with Cv. Cv, you count the number of degrees of freedom. Now, they said we had argon. Argon is one of the noble gases. It is not diatomic. It's monoatomic. All it can do is go left, right, up, down, and forward, back. So this would be then 3/2 R for Cv, which means Cp would be 5/2 R, which then means we have 5/3, which is about 1.67. So this is 1,073 raised to a power of 5/3. Okay. Now, the initial pressure was the 1,500,000 pascals. That's the 1.5 megapascals. And we're going to raise it to a power of 5/3 minus 1. And 1 is a 3/3. So this is going to be just 2/3 left over. And then also here, final pressure is going to be 300,000. Oh, let me look. Is this gauge pressure or is this absolute pressure? I better look here. Argon temperature at a pressure of. They just say pressure. They don't say absolute, and they don't say gauge, but I think they mean absolute. Okay. And then also exits at a pressure of. And again, I think they mean absolute there. Okay. So these don't have to add the atmospheric pressure because I don't think they're saying gauge pressure. But now that it's 300,000, again, I've got a gamma minus 1, and so that would be 2/3. So maybe I'll just do this in 2 steps. This is final temperature to the 5/3. Let me grab my calculator. I'll do this one on the bottom. This is 300,000, 1, 2, 3, raised to a power of 2/3. All right, so that's that number, which I'm going to bring to this one and multiply it. So times the 1,073 raised to a power of 5/3. Okay, then all of that divided by 1,500,000 raised to a power of 2/3. And as an intermediate step, then I will write this down as 38,461. So then the final temperature, I would say let's raise both sides to a power of 3/5. Okay, so raise it to a power of 3/5. And so this comes out to be a final temperature of 560, and I'll go 4. And I've done everything in absolutes, and so this would be Kelvin. And so there's the A. What is the final temperature? Okay, then so B says calculate the maximum power output of this turbine. Okay, well, to get that, we have to talk about the energies. And I'm going to go to the first law of thermodynamics and figure out how do I calculate the work being done. And the fact that they said it was adiabatic means that I can cancel off the Q, because there is no heat in an adiabatic process. And so the work equals the change in internal energy. And internal energy always equals the number of moles times the CV times the delta T. Now that's looking good because the delta T I do have. I do have the beginning temperature and the ending temperature. So that's all really good. And so that's the work. Now if I divide the work by time, now I can begin to answer their question about the amount of power, because the power is this energy per ton. And this right here would be the number of moles per time going through our engine. So let me come back up here to this kind of little picture I was drawing at the first. Remember I said this is telling you how much mass per time or per minute goes through, but that is also indirectly telling you this ratio, the number of moles per time. So maybe I'll take a moment and calculate the number of moles per time. So putting this as 80 kilograms per minute, which I'm going to write as 60 seconds, that is the number of kilograms per second. But then if I look up the molar mass of argon, and so I've got my little periodic table here, looks like it's 39.9 grams per mole. So I'm going to put 1 mole is 39.9 grams, although I'm going to convert it into kilograms. So there's the atomic mass on the periodic table, the 39.9, and I'm going to move it 3. So that's how many kilograms it takes to make a mole. So that's why if you take the 80 kilograms and divide it by that number, that tells you how many moles you have. And then the moles per 1 minute becomes now the number of moles per second. Okay, so this across the top is 80. Then across the bottom is dividing by 60 and also dividing by 0.0399. And it looks like we're looking at 33.4 moles per second. That is going through this, probably a pretty large turbine engine here. Or, yeah, functioning pretty high. Okay. Now, that is the number I'm going to use back up here, number of moles per second. So that's the 33.4 moles per second. Now, CV, as we did back here on page 1, we got to look at what kind of gas. Again, they said argon. Argon is monatomic, so this would be 3/2 R. So right there, I'm going to put 3/2 R, and R is 8.31 joules per mole Kelvin. And now the change in temperature, and so final is 564 Kelvin. And initial, we said, was in Kelvin, 1073. That's the 800 degrees Celsius. So 1073 Kelvin. That way, Kelvins will group together and cancel off moles, and we, of course, will be left with units of joules per second. And so that'll be the number of watts. Okay, so I've got the 33.4 already in my calculator here. Let me multiply that by, looks like 3 over 2 is 1.5. Let me multiply that by 8.31. And let me multiply that by 564 minus 1,073. And it looks like we are looking at a negative 212,019 watts for the power. The minus sign is good because that means it's coming out of the gas. And that's the whole point of an engine, is that it comes out of the gas and goes into the engine and makes the engine go, whatever this turbine is. Maybe this is, it sounds a little bit like it might be the engine of a helicopter, although argon gas wouldn't be used for that. But minus that fact, we've got a extremely powerful turbine engine, and that's nice about a turbine engine, is it's a lot of power in a short space and lightweight. Huge amount of maintenance, so wouldn't put it in a car. You'd spend more time maintenance on your car than driving your car, but that's what you do with a helicopter. You spend more time on maintenance than flying it, and a tank too, you know. You got to have all this power, but you got to spend more time on maintenance than actually driving the tank. Anyways, there is our power. And let's see, what was the third part? The turbine is one component of a modeled closed-cycle gas turbine engine. Calculate the maximum efficiency. Now, maximum efficiency was done by a guy named Carnot. So we call this the Carnot cycle. Now, this engine, we don't really know what the process is. They just say this one is adiabatic. We learned that the Carnot cycle has 2 adiabatics and 2 isotherms. The isotherms are very time consuming. So the reality, you don't really build engines with a Carnot cycle, because what you gain in efficiency, you lose in power, because you got to spend so much time on the constant temperature part of it. But at least it gives us a goal to shoot for. And factoring in entropy is the whole point, is then that the Carnot cycle has this efficiency. And we know that no matter what we do, we cannot do better than this efficiency. So when we're building our heat engines, we kind of shoot for how close can we get to this efficiency. By the way, we already know we're never going to get 100% conversion of thermal energy into work because of the requirements of the second law of thermodynamics. And by the way, the first law of thermodynamics tells us we would never get better than 100%. So we never, as engineers, shoot for 100%. We shoot for what the Carnot cycle is. The Carnot cycle is taking into account not only the first law of thermodynamics, but also the second law. If you only think about the first law, you kind of shoot for 100% efficiency, and that's just a mistake, because nature won't let you do that. But the Carnot cycle puts together both the first and the second law, and gives us something to shoot for. So in this particular engine, the cold temperature is 564, and the higher temperature was this 1,073. So if we're going to be operating at these particular temperature values, we should be aiming for an efficiency of 1 minus 564 over 1,073, which is about a 47.4% efficiency. So when we actually build this engine, we can then measure our efficiency. And let's say we come up with 40%. We would probably be pretty happy with that. We'd go, wow, we're not, at the best efficiency, but we're pretty darn close. And maybe we can get even closer. But in something like this, we would not try to even attempt to get to 50% efficiency. It's just a against the laws of nature. And so that second law was really a hindrance in terms of making things efficient. And too bad, but we don't make the laws, we just have to follow them. So these are the laws of physics, and this is the best this engine can do. And that's the end of the problem. Hope you enjoyed it.